Welcome back. In topic 1, we discussed the heat transfer mode in terms of conduction, convection, and radiation. In topic 2, we will learn how to calculate heat rate and heat flux for each heat transfer mode. A. Heat equation for conduction. First, let's look at our system. We have a solid plain wall with a thickness of L. The left surface at a temperature T1. The right surface at a lower temperature T2. Both surfaces have the area A. Since there's temperature difference, then there's conduction heat flow. And its heat rate can be calculated by area A, which is perpendicular to the conduction heat flow, divided by the thickness L times the temperature difference from these two end surfaces. The temperature difference unit can be Celsius or Kelvin, then time thermal conductivity K in the unit watt per meter per Celsius. What is thermal conductivity K? Assume we have a piece of steel and a piece of wood. Now, we put fire on the top of both surfaces. The question is, which hands will feel the heat immediately? The answer is the hands holding the steel. From this experiment, we learned that different materials like steel and wood, they have different ability to conduct heat through each material. This kind of ability is measured and represented by the thermal conductivity K. As a result, steel is a good heat conductor, and it has a larger thermal conductivity value. Wood, on the other hand, is a heat insulator, and its thermal conductivity K value is smaller. Second, if we're interested in the heat flux, which is a conduction heat flow through a specific point at the surface area A, the equation 2 can do the honor. Do the calculation. Third, heat equation for conduction is based upon Fourier's law. B. Heat equation for convection. First, let's look at our system. We have a heated plate surface at a temperature Ts and an area of A. There is cold fluid passing over the plate. Since there's temperature difference, then there's a convection heat flow. And its heat rate can be calculated by area A, which contacts the fluid, time the temperature difference between solid surface and fluid, time heat transfer coefficient H in the unit watt per meter square per Celsius. What is the heat transfer coefficient H? Assume we use a fan blow the cool air to cool down the hot egg. If we increase the speed of a cool air, more heat from the hot egg surface through convection will be carried away. From this experiment, we learned that fluid at a different speed has different ability to deliver convection heat. This kind of a ability is measured and represented by the heat transfer coefficient H. As a result, low-speed fluid has smaller value of heat transfer coefficient. On the other hand, high-speed fluid has larger heat transfer coefficient. Second, if we're interested in heat flux, which is heat flow, convection heat flow at specific point of solid surface area A, equation 2 can do the calculation. Third, all the heat equation for convection is based upon Newton's law of cooling. C. Heat equation for radiation. First, let's look at our system. We have a small solid surface at temperature Ts and area As. It is surrounded by a large surroundings at a temperature T surrounding and area A surrounding. we assume the solid surface area is much, much less than the large surroundings area. For example, the surface area is 1 meter square. The large surrounding surface area is 100 meters square. So the solid surface area mathematically is much less than surrounding surface area. Since we have temperature difference between a solid surface and a surrounding, then there's a radiation heat flow. Its heat rate can be calculated by the solid surface area AS time a Stefan-Boltzmann constant time temperature to the fourth power difference. And in this equation, the temperature must use Kelvin. Then time solid surface emissivity epsilon. It has no unit. Its value is between 0 and 1. What is surface emissivity? Assume we have a steel pot and a same size of iron pot. Now we set fire for both pots. After 5 minutes, which hands will feel the heat? The answer is iron pot. The answer is the hand above the iron pot. From this experiment, we learned that different material surface has the different ability to deliver radiation heat. This kind of a ability is measured and represented by the surface emissivity epsilon. As a result, the steel surface has a smaller value of emissivity. Iron, on the other hand, has a larger value of emissivity. Second, if we're interested in heat flux, which is radiation heat flow at a specific point on the solid surface area, equation 2 can be used to do the calculation. Third, heat equation for radiation is based upon Stefan-Boltzmann law. At this point, we covered topic 2. If we do a quick summary, here is the key point. We provided 6 heat equations for heat rate and heat flux, and introduced 3 new variables: The objective of topic 2 is for you to be able to apply the heat equation to the heat transfer problem. Next, let's practice. Again, remind you a piece of advice. For each example, you should try on your own, then compare your notes with the instructors. Oh, okay. An insulated steam pipe, so this is a steam pipe, carry the steam. It has the length of 1 meter and diameter 70 millimeter. It has the surface temperature 200 degree and emissivity of 0.8. This pipe passes through a room, and this symbol represents large surrounding of a room. It is at temperature 25 degree. And air at temperature 25 degree with heat transfer coefficient 15 passing through the outside of the pipe. We're interested in finding the convection heat loss rate and radiation heat loss rate. For heat transfer problem, where do we start? We start with identifying the heat transfer mode. Since we have temperature difference between solid surface with another solid surface without direct contact, then there's a radiation heat flow. Since we have temperature difference between solid surface of pipe and moving fluid, then there's a convection heat flow. And the heat loss from the pipe surface, of course it is outside surface, is through convection and radiation. The area in fact is pi dl. Since we knew the heat transfer mode on the outside pipe surface, we can select the heat rate equation for convection, which is the heat transfer coefficient times area. The geometry is cylinder or cylindrical, so the area is calculated by pi dl. Then at time the temperature difference between solid surface or pipe and moving fluid air. Then you plug into the number for heat transfer coefficient H, for the area, then for the temperature difference. Finally, you get the rate or convection heat loss from the surface of the pipe. The second heat loss is from radiation. So you can select the radiation rate equation, which is emissivity time the surface area time the constant time the t to the fourth power difference. Next, plug into number, type surface emissivity, area, Stefan-Boltzmann constant with unit, then time the difference in the temperature to the fourth power. You have noticed the temperature already converted from Celsius to Kelvin. Finally, you get the rate of radiation loss. In summary, this example showed you the steps. You start with identifying heat transfer mode, then select the proper equation, finally plug into number to get answer. See you next time.